All right, so here we go. This is a problem similar to one we just worked, a little more detailed. You see, you want to find the maximum positive moment that can be developed at point D. Now, this one has a little bit something different in it. You'll notice that you have a live concentrated load of 4 kips. You have a dead load of 200 pounds per foot. And now, this is something a little different. You have a uniform live load. So we haven't talked about that yet. So this will be something a little new to the problem. Since it's live loads can move around. So we're going to position this uniform load on the beam where it will do or create the most, in this case, a positive moment. So that'll be something a little different. So our first step is going to be to what? Draw the influence line for the moment at D. So that means I would come to D, imagine a hinge there, and then apply a positive bending moment to both edges. And let's see how we think that will move. So give me a second to draw the template. So this will be the moment at D. And we're in kips and feet, so this will have units of feet. And then let's bring down all these important points to help us make sense of the diagram. All right, there we go. So now let's go back to the Munell-Brezov principle. So I've imagined this hinge here, which has no moment capacity. Now I'm applying moment. So is point D going to go up or down? It's going to rotate up. So if it comes up to here, let's say, then it'll go like that. It'll hinge at D. It'll seesaw over C. Then the hinge at B will allow it to rotate back up and connect at A. So there's the shape of my influence line. So the two obvious points that would be easiest to find the moment for was within the remember this is the uniform load position X. We could either put it here at B and find this value, or we could slide it over to D and find this value. I don't see a real big difference. However, you can't draw a single free body for the whole structure. You're going to have to take it apart. You're going to have one free body AB, a second BE. So if you apply it at D and the load is here at D, then there'll be no loads on AB, and I think that'll be an easier approach. So I'm going to look for the situation where our moving load, our unit load, is positioned at D. So let me redraw that in that position. So I've got my AY, I've got a hinge, I've got a roller at C, and then a roller at E. And then I'm going to put my unit load at D, which is about right there. And that would give me the dimensions of 5 feet, 5 feet, 5 feet, and 10 feet. And that's point D. That's where I want the moment. So ultimately, I'm going to come back and cut the structure right there. So looking long term, do you want to work the left side or the right side? Right. Yeah, I think the right side is going to be easy. So if I work the right side, I'm really interested in EY. So how am I going to find EY? Well, I think the first step will be, I probably should have labeled this A, B, C, and E. So I'm going to look at the free body diagram. I'm going to take it apart here at B, and I'm going to look at this side. But I'll draw both just so you can see it. So here's AB, and there would be a reaction at A. And I'm going to assume that there would be a shear force at B. Of course, equal and opposite on the right-hand side, my shear would be up. That's the same value, the shear at B. And then I would have my reaction at C. I'd have my reaction at E. And then, of course, I've got my unit load sitting right there. So again, look at the dimensions. This is 5, 5, 5, and 10. Now remember, my target right now is EY. So if you look at this free body diagram, this would be the free body diagram of AB. Well, there's no load on it, right? So all these forces are 0. So I know right away that B, the shear at B is 0, so the shear at B is 0 here. So looking at this free body, and I want to find EY, where should I sum moments?
C.
C. So if I sum moments at C, well, I know the shear at B is 0. I've got this unit load. What kind of moment does that create about C using right-hand rule? Negative. So I'll have -1. Remember, it has no unit. Moment arm of 5. EY creates positive moment. So there's the force. Distance from C to E is 15. So it looks like EY is 1/3. Again, no unit. Okay? So now I can actually cut it here at C, and when I do that, it looks like this. So that section is 10 feet long. I know my reaction at EY. It's 1/3. And then here is the moment at D. Of course, there's shear there too, but we're not concerned about that. We just want the moment. So all you have to do now here is some moments at the cut you just made. The internal moment is negative. The 1/3 creates positive moment with the moment arm of 10. So it looks like the moment at D there is 10/3. I'll just leave it like that. And that would be feet. So that means this value here is 10/3. If this value is 10/3, what's this value here? Yeah.
Why do you not consider the shear at B when you took the moment at C?
Well, we already found that if you look at this free body diagram, what's the shear at B? 0. So when it's 0 here, equal and opposite over here, it's 0 too. Remember, this is 5 feet, so 10 over 3 is to 5 as what is to 5? 10 over 3. So this becomes negative 10 over 3. And now you've got all the values for your influence law. And now we can solve the problem. Mr. Markle, you have an answer? You have a question?
Wouldn't that be negative 2/3?
One of these is positive. This is positive. Sorry. Yeah.
So, in this case, it wouldn't matter. But how do you not have the 1 here?
Well, I could put the 1 there if I wanted to.
Okay. Because if you were finding shear,
But we're not finding shear yet. So now we can do all the parts. So let's start with the live load. Also, we want to find the maximum positive moment, right? So you can see there's a negative area and there's a positive area. So since I want the positive moment, I'm going to use the positive value. So the largest positive value is 10/3 and occurs at D. So when I do my live load, I'm going to take the 4 kip force and I'm going to multiply it by positive 10/3 feet. And when I do that, I get 40/3, which is 13.33. Is that right? So that'd be 13.33, and that will be kip feet. So that's the moment due to that load, and it'll actually happen here at D. Let's do the uniform dead load. We've done a couple of these. That uniform dead load is 300 pounds per foot. I'll go ahead and convert it to
200 for the dead load.
200. So I'll convert that to kips. That'll be 0.2 kips per foot. And now I have to multiply that by the total area under the curve. So there's a negative part and a positive part. So I'll keep those separate. They're both triangles, so they'll have the 1/2 out in front. So looking at the negative area, it'll be a base of 10 feet and a height of -10/3 feet. That's the negative part. Then plus the positive part, which has a base of 15 feet and a height of 10/3 feet. I don't know what that's going to be. Let's see. 50/3, 25/3, 5/3. 1.67. So that's kip feet, and that's also positive. Now the new thing. Uniform live load. Live means it can move around. So think of a dead load or a uniform load that can start and stop, start and stop, start and stop. Where would you start it and where would you stop it so that it would cover the maximum positive area of your curve? It would start here at 10 and it would go off at E. If you covered it, if you let it go over the first 10 feet, it would generate what kind of response? Negative. And we're trying to find the maximum positive moment. So you only turn it on in the areas where it's positive. If we were finding the maximum negative moment, we would have a completely different loading scenario. Your unit load would be here. Of course, the dead load would be the same. You can't control that. But where would the live load be then? It would be over the first 10 feet. So let's compute it for this case. The uniform live load is 300 pounds, so that's 0.3 kips per foot. Again, it's a triangular area, so 1/2. In this case, the positive base is 15 feet, and the positive height is 10 feet over 3. $5.50, $25. 0.75. I don't know. 7.5. I'm guessing.
So the instructions were to say determine the maximum moment.
Maximum positive moment.
No, I know. Here it says positive, so you only take the positive. But if it were just the same moment, and
you'd have to do both cases and check it.
Okay.
That's a good point. So be careful if we do end up with some mastering engineering problems, and they say what's the maximum moment. Remember, sign is just direction. So they mean the magnitude. So it's possible that you could have a larger negative moment than positive moment. That doesn't mean the positive is not always greater than negative. The sign is just direction. So it's magnitude. So they say what's the maximum moment? It could be a maximum negative moment or a maximum positive moment. You have to check both cases. What would that come out to be?
7.5.
So now we just have to add them all together. So therefore the max moment at D, well, that's convenient. Those add up to 15. Looks like 22.5. Now, what does that look like? So let me, again, I'll redraw the beam, and we will... so here we have a pin, and we have a roller. We have a roller. So remember, the dead load goes across the whole structure. Can't do anything about that. So there's the dead load. The dead load in this case was, that's 0.2 kips per foot. Now the uniform live load only went from C to E, so that would be here. And that has the value of 0.3 kips per foot. And then where did our live concentrated load end up? Right at D, which is kind of here. And that had a value of 4 kips. So that's the load combination that creates the maximum moment of D. Positive moment of D.
Will you be looking for us to do that on the test?
Do what?
To draw out that diagram?
No, sometimes I think it helps you see it if I draw the diagram. Dead load goes across the whole structure. Live load can be wherever you want it. And then, of course, the same thing with the concentrated load, wherever you want it. But again, I could ask you for the maximum negative moment, and we get a different load pattern. And we get a different value.
So when it states we have a uniform live load, we need to go back into the problem and find out exactly what it's asking for.
Well, when you have a live uniform load, whatever you're looking for here, reaction, shear, moment, whatever, if you want the positive value, you're going to position it over the positive areas of the curve. If you want the negative areas, you do it here. Dead load is the whole beam. So you can see in our case, the dead load always produces a positive moment. You can't do anything about it. But when I position the uniform load, the live uniform load just here, I'll produce a negative value. And when I move my concentrated load of 4 kips to be here at B, I'll produce a negative value. So I'll end up probably with a negative moment, but it'll probably be smaller than this one. So that might be the maximum moment at D, but there would be a negative moment created too for a different load combination. Okay, super exciting, huh? All right. Oh. Stop.